Seriously, my bad. Hold on, do apologize. I just want to copy the picture, please. Yes. Right. Now we have to calculate at, the question, this question is pretty straightforward. It asks you to calculate point A. Okay. Now, if it's not given, we cannot assume that point A has the highest shearing stress. At point A, what it has the highest what? It has the highest what? Q max. Yes or no? The first moment of area is highest because at point A, now it becomes what? At point A, now it becomes non-thin wall. Yes or no? So at point A, the area that we have to consider is this now. That is the entire section. So it has the highest what? Area. But it also has the what? Highest thickness. Yes or no? Right? Whereas at point B, right? At point B, right? Q max, it just has a Q value, not necessarily the maximum. And the T is not necessarily maximum, right? And then at point C, T is what? Minimum. Yes or no? Right. But what we realize when we calculate the shear stress, right? When we calculate the shear stress, okay, when we calculate the shear stress, you realize that the thickness at point C is the smallest, right? At point B is bigger. However, the area is 22.4, 22.5. Over here, your area is 77.5 times 10 to the power minus first mole of area. That is why this value is higher at point where? At point B for now. So now the next one we're going to check is at point A is where the maximum Q max. Okay, so we're going to find Q max now. So we will look at Q max. So we are going to analyze point C, shear stress at point A, sorry. So point A is non-thin wall analysis. Okay. Anyone online you have question, just ask. Okay, you can type. Okay, everyone can hear you. Don't just sit back there. Okay, and no sleeping. Yeah. Okay. So non-thin wall analysis. So now we know that T is equal to 0.12 meters. Okay, T is equal to 0.12. So from here, we are going to find shear Q at point A, which is also equal to your Q max. So then you have to take twice of 77.5 times 10 to the power 3. Okay, so why twice is because of the right web or the right part and the left part. Okay, then we plus, by the width will be equal to 120. The depth will be 30. The Y bar will be 30 divided by 2. So 120 times 30 times 15 plus by 2 times 77.5 power 3 is equal to 209 times 10 to the power 3. Millimeter cube, or 209 times 10 to the power minus 6 meter cube. Okay. So from here, the shear stress at point A now, Vy over Izz. Okay. Then you multiply by shear stress at the first moment of area at point A. thickness now is divided by 0.12. So 209 power minus 6 divided by 0.12 is equal to 209 power minus 6 divided by 0.12 is equal to 209 1.209 power minus 6 112. You get 1.741 1.742, sorry, times 10 to the power minus 3 Vy over Izz. Right? So you realize that shear stress at point A is not the biggest. Okay. So finally, therefore, shear stress at point B is equal to your tau max, which is equal. So tau max given in the in the question is 75 times 10 to the power 6. So this will be equal to Vy over Izz, and then 3.875. So from here, we know that Vy over Izz is equal to 75 power 6 divided by 3.875 power minus 3. So 19.355 times 10 to the power 9. Okay, let me do it again. 3.875 power minus 75 power 6 divided by 3.875 power minus 3 is equal to 19.355. Okay, and then the units is in Newton per meter to the power 4. Okay. So from here, we can directly calculate our shear stress at point A and our shear stress at point C. Okay. So what I'll do, rather than flipping here and there and here, okay, I will draw a box. Now do the working in there. If not, I get a headache. You will do the same. You'll get headache. So shear stress at point C is equal to 2.25 times 10 to the power minus 3 multiplied by 19.355 times 10 to the power 9. Okay. So it's equal to 19.355 power 9 times 2.25 power minus 3 is equal to 43.549 times 10 to the power 6 Pascal. I'll do it again. 19.355 power 9 times 2.25 power. Yep. And then the shear stress at point A will be equal to 1.742 times 10 to the power minus 3 multiplied by 19.355 times 10 to the power 9. So this will become 1.742 power 3 times 19.355. 1.742 power minus 3 times 19.355 power 9 is equal to 33.716 times 10 to the power 6 Pascal. Okay. It's not that bad, right? Okay, it's pretty straightforward, I hope. Any questions so far from anyone? Online, no one is asking question. Anyone? No? Okay. Now my next question is, since now you know how to design the shear flow, right? Okay, I can see. Let me, yeah, someone is still copying. Okay, now I will not do it, but I want you to have the confidence. Okay, I can see some of you have confidence. Okay, I can see that. So now if this is Y and this is Z, what will happen now if this is the case? Now the forces, the shear force is coming in the horizontal direction, right? So you still apply the same rules that I mentioned. We still apply the same rules that I mentioned, right? What do I mean by that? The shear flow is called, now this is the web, right? The shear flow is coming down this way, right? And then fluid or the shear stress will be coming in this way, and then will be going up this way. Okay. So now your formula becomes the shear. So now this is a shear x plane. Hey, when I say x, I write z. The shear x plane, okay, in the, let's not look at direction yet because it can be complicated depend on where we are. I just write the general formula. So the shear stress is equal to Vz over Iyy Qy divided by T. All right, so now we are looking at the what? Now we are looking at the, our centroid now is on the YY axis. Okay. So this is our centroid now. Okay. I will just show you the first moment of area calculation. Okay. So the first moment of area is different when it is on, when it's Vy, right? So now this is the, so now we want to find at point C. Okay, at point C. And at point C, I will just write this down. It is a white flange analysis. Okay. Why white flange? Because the ending terminal of the dot I've just drawn and the dot below, they are in separate terminal, yes or no? So it's a white flange analysis. So it's still going to be Q. Now the thickness is going to be what? Thickness is still the same, 0.01. Okay, and then we calculate the first moment of area now. Okay, so the first moment of area Q at point C now, right? So now this becomes the width, this becomes the depth. Remember what I taught you about finding first, second moment of area? The axis that is parallel, the geometry, well, the axis where the geometry is parallel to the axis of interest. The axis of interest now is the YY axis. Okay, so any geometry that's parallel to the axis is your width. Anything that's perpendicular is your what? Is your depth, right? So this apply for second moment of area. This also apply for what? First moment of area. Then you will not get mixed up. So in that context, so my width, our width now is 10. The depth now is what? 30. And then the distance from here to here. So this distance is what? This distance, this is equal to 60, right? The distance from here to here is equal to what? 40, right? And then we have a gap. The gap is 10. Okay, so the centroid is equal to, I'm just going to apply the formula. It's equal to 40 plus 10 divided by 2. Okay, or, oh, someone on his mic. 10 multiplied by 30. If you can work the dimension straight, so it's 20. Wait, it is 40 minus pi. So because this is 60, 40, 50, 20, 30. Wait, I'm a bit dazed now. So this is 10, 30. This is 30. So it will be 40 minus 30 divided by 2. So the answer should be the same. I can be wrong down here, okay? 40 plus 10 times 0.5 times 30 times 10. So it's equal to 7500. Or 40 minus 30 divided by 2 times 10 times 30 is the same, 7500. Or okay, so the first moment of area is different. As you can see, when it is, I should write down here, the first moment of area about the y-axis at point C. Okay, now you guys will ask me, Eugene, where did this formula come from? Right, this formula come from when we were doing the what? Remember when we were deriving this? Right, this is C, right? So to find your centroid of this area, right, your y bar, this is your y, right? So the y bar is equal to C plus y multiplied by what? Half. That's how I came up with that, okay? So again, you go to the same procedure. I'm not going to do the rest, okay? It's so straightforward, but you have to be aware of this now, is that your first moment of area now is taken about your what? Your y-axis, okay? You just have to be aware of it. Okay, let's look at another example, okay?